Okay, so this is another video about applications of vectors and vector properties, and one of the applications that you'll see is a sum of forces application. So you might have a picture like this. They tell you that you've got some cables hanging from the ceiling, and then you've got another cable hanging off of that, and it's carrying a mass. And maybe they tell you the mass itself, or maybe they tell you the weight. Maybe they say there is a weight of 100 pounds hanging here. And I've got a cable here and a cable here. And they might ask me to find the tension in each cable. It's just another version of force. It's force. And we're assuming that this mass isn't moving. Now, the fact that we need from physics is this. The resultant force acting on an object is the sum of all the individual forces acting on the object. So if there are 5 forces acting on it, I just take all 5 of them. There's not even enough room on here. If there are 4 acting on it, I take all 4 of them. These are vectors. I add all these vectors together and I get the resultant force. And then we know from Newton's laws, well, force is equal to mass times acceleration. So mass times acceleration is equal to this over here. I could use this to find the acceleration. There are lots of things that we can use this for. But in this problem, notice that you've got a weight that's hanging here. We want the tension in the cable and nothing is moving. If nothing is moving, that means acceleration is 0. So I need the sum of forces in all of the directions. I need that to be the 0 vector, which means the sum of the forces in the x direction has to be 0, and the sum of the forces in the y direction has to be 0. Now we're using these subscripts to indicate direction now. We're not using them to indicate other things like the components or anything like that. So keep that in mind. This is sum of forces in the x direction. And this is sum of forces in the y direction. This is just shorthand. If you've had Physics 1, you've seen this before, no big deal. All right. So I need to find all of the forces that are acting on this system. Well, first of all, I've got my weight. They told me that that was 100 pounds. That means if there's a cable here, that's going to be 100 pounds to balance that. That means there's going to be 100 pounds to balance that. And there's some tension in this cable, and there's a tension in this other cable. Now I'm going to draw a line that is parallel to the ceiling so that I can split those 2 tensions into their components. First of all, it might be helpful to figure out how these angles relate. If that's 59 degrees, what's that? Isn't that just going to be 90 minus 59? Because that's a 90. So that's going to be 90 minus 59. If that's 90 minus 59, what's that? Well, the total is 90, so that's going to be 59. So there's a 59 degree angle right there. Or you might remember that relationship between the angles from high school geometry. It's okay if you don't. Similarly over here, that's 90 minus 35, so that means that has to be 35. And I want the tension on this guy and the tension on this guy. I'll call them T1 and T2. And they're vector quantities. Now they asked us for the tension. In this class, if someone asks you for the tension, they're not just asking you for the magnitude. When they say find the tension, they mean find the tension vector. So the tension as a vector, the x and y components of this tension and the x and y components of this tension. And usually we want the magnitudes too. I will be more explicit on your quiz over this material. Okay, so I am going to use this symbol for the tension over here, and this symbol for the tension over here. And we're going to break it into components. Because I am in Calculus 3, rather than just using T sub 1 without a vector, without an arrow over it to indicate the magnitude of the tension, I'm going to use that magnitude notation. This is the magnitude of T1. I know it's overkill in the notation, guys. I know if you've taken physics, you're like, there's a much easier way to write this. I know. But we're in Calc 3 and we're getting used to this new notation, so we're going to keep using it here. Okay. Now, I know that the sum of forces in the x direction and the y direction have to be 0, so I'm just going to split these forces into their component parts. Now this, my coordinate system, my x-axis and my y-axis, they can go anywhere I want. I can pick the direction and that's fine. Everything is relative, right? So I'm going to choose this to be my positive, or this to be my x-axis, this to be my y-axis, and this to be my origin point. And that is a matter of choice, but it's a convenient choice, because with that choice, I can split this tension T1 into two parts. There's part of it in the x direction, and there's the other part in the y. So let's talk about the tension through T1. Well, the x component of that tension, that's adjacent to the 59. It's going to be whatever the magnitude is, which I don't know, times cosine of 59. The adjacent side gets the cosine. It's in the positive x direction, so this is going to be positive. And then opposite the 59, I get the sign. That's the y component, and it's going in the positive y direction. So that's one force acting on the system, broken up into its component parts, the magnitude times cosine and the magnitude times sine. And we can do the same thing for T2. And I have a magnitude times a cosine, and that should be a 1. That's going to be a big old mistake if I had that wrong. Magnitude times sine over here. Be careful on this one though. These are not angles measured from the positive x-axis. I know you could say, well, if that's 35, then the angle must be 180 minus 35. You could do that if you wanted to, but there's a much easier way. If you see that 35 there, and it's going in the negative x direction, just say, well, the side that's adjacent to the 35 is going to get the cosine of 35. But it's in the negative x direction. So rather than subtracting that 35 from 180 and getting the right angle, I'm just going to put a negative there. That negative takes care of the fact that that's over there, as opposed to that angle that's that one over there. So just choose the right sign based on your choice of origin. That's the negative x direction, so I get a negative here. That's still positive y direction. So we're going to have the magnitude of T2 times opposite the 35 is going to give me a sine of 35. So those are those two forces, and then we've got this other force from the mass that's pulling down. We've got 100 pounds. The weight of that mass is 100 pounds. There is no force acting in the x direction there at all. It's all in the y direction. It's just 100. Okay. Now, the sum of these three vectors has to be 0. This plus this plus this is the 0 vector. And if I add component by component, I get this. Oops, and that weight is pulling down in the y direction, so that should be a minus 100. And then you're going to say to me, so many are going to say, Miss Townsend, there's a faster way from my physics class. You're absolutely right. Why do this to yourself? If this is the 0 vector, the only way that this is this vector, which is the vector 0, 0, is if this is 0 and this is 0. Isn't that what I told you earlier? The sum of forces in the x direction has to be 0, and the sum of forces in the y direction has to be 0. And if this is 0, well, that's just a number and that's just a number. I can figure out what t1 is in terms of t2. And once I know that, I can substitute that in over here, and I can solve this one for just a single variable. So it's actually pretty simple from here. It only looks worse because of the trig functions and all the magnitudes and the vector symbols, but it's actually very, very easy. We've got two equations and two unknowns. Sum of forces in the x direction, and sum of forces in the y direction. Forgetting my vectors and my magnitude stuff, sorry guys. It's very important. Sometimes I forget to. Alright, so I'm going to take this one, I'm going to solve it for, let's say t1 in terms of t2. So that's my first equation. I'm going to add this to the other side. I'm trying to get this guy by itself, so I'll divide both sides by cosine of 59 degrees. Alright, so I know t1 in terms of t2. So I can replace the t1 right here. I can replace that with all of this, and then I'll have one equation and one unknown. It'll involve t2 only, or the magnitude of t2 only. So I had t1, which was this, times sine of 59. If you want, you could call that sine over cosine of 59 a tangent of 59. That's totally fine. Plus the other guy. And we had a minus 100. I'm going to add that to the other side. I'm trying to get t2 by itself, so I'm going to factor it out. It's just algebra 1, guys. Nothing fancy. It looks worse than it is. And cosine of 35, tangent of 59, plus sine of 35. Woo! Divide by all that. Alright guys, so I'm putting in my calculator, 100 divided by open parentheses, cosine of 35, and I am in degrees, that's good, times tangent of 59, plus sine of 35, close parentheses for the sine, close parentheses for the denominator, hit equals or enter, and we get an approximation. Magnitude is approximately, let's say 51.6. The weight was in pounds, so we're going to have pounds there. Now that I know T2, I can use the fact that T1 equals this to find T1. So T1 was the magnitude of T2 times cosine of 35 divided by cosine of 59. I've got that in my calculator already, so I'm going to multiply by cosine of 35. And then divide by cosine of 59, and I get 81.1 or 82.1 approximately pounds. Gosh, I hope that works out. All right, so let's go back to our problem. This is what it looked like roughly. T1 looked like this. That was 59 degrees, obviously. This is not to scale, and this was 35 degrees over here. And T1 is the vector. It looks like this. This was T1. It's that magnitude times cosine of 59. And the magnitude times sine of 59. I keep putting a 2 there. So I get approximately 82.1 times cosine of 59, and 82.1 times sine of 59. I'm sorry, my picture is so bad. 59 degrees is going to be up here. It's going to be, it's closer to 2/3 of 90, not whatever that is. So let's figure that out. Approximately 82.1 times cosine of 59. It's approximately 42.3 pounds in the x direction. And then I've got that times sine of 59. It's approximately 70.4 pounds in the y direction. Okay. And T2 looks similar. We had a cosine of 35, but it was negative because it was going in the negative x direction, right? And the magnitude of T2, according to our algebra up here, was 51.6. And let's make sure everything is what it's supposed to be. After we do this, let's see if everything makes logical sense. I've got negative 51.6 times cosine of 35. It's negative 42.3 approximately. It's pounds, but pounds are units of force and it's pulling us that way. That's why it's negative. And then the 51.6 over here times sine of 35 is 29.6 approximately, also pounds. Okay, so let's think about this. Let's think about if these answers make logical sense. I'm never 100% sure on this, and that should be approximate. I can't be sure that if I pull in this direction with a force of 82.1 and I pull in this direction with a force of 51.6, that's exactly going to balance the force of 100 pounds pulling down. I'm not 100% sure, but this is what this tells me. They say T1 is pulling 42.3 units in this direction. That's how many pounds of force are pulling this way. And T2 is pulling with negative 42.3 pounds of force that way. So does that balance that? Yes, and that's good because the thing's only moving up and down, right? It's actually not moving at all. But the sum of forces in the x direction is 0. Since we're not moving to the left or to the right, there's no tug of war. Everything is balanced out. Those two should be opposite of each other, and they are, so that's a very good thing. The other thing was these two forces, this force that's pulling up here and pulling up there, when I add those two together, it better balance this 100, because if I'm pulling up like this and pulling down like that and things not moving, well, the only way that works is if I've got 100 pounds of force pulling up and 100 pounds of force pulling down. It's like a tug of war. If any of them were larger, well, we'd be going, we'd be moving. Is 70.4 plus 29.6, 100 pounds. I mean, of course, these are approximations. But yes, it turns out even when we round, that's about 100 pounds of force pulling up. So it's 70 pounds of force pulling up over here and 29 pulling up over there. You add them together and approximately we're getting 100, and that's balancing that 100 pounds of force pulling down. So we answered the question. There's the first one. There's the second one. And we're done. Now in the class notes, there is an example of this that's 3D. Instead of just forces that are acting in an XY plane, you've got forces all pulling in 3 different directions. You're going to do the same thing though. We had this, 2 equations and 2 unknowns, sum of forces in the x direction and y direction, that's it. For in 3D, you're going to have sum of forces in the x direction, y direction, and z direction. You're probably going to have at least 3 unknowns, 3 equations and 3 unknowns. You're going to have to solve that system instead. It's going to be a little bit more involved, and again, I know this looks like alphabet soup, but this is nothing that you can't handle. This is just a system of 2 equations and 2 unknowns. It's algebra. The notation, the trig functions make it look bad. But this is just like solving like 2x minus 4y equals 7 and negative 4x plus 5y equals 1. If you can solve this, you can solve this. And it's even simpler than that. It's like if there was a 0 over here and it's really easy to solve for this and then substitute it into the other one. It's exactly what we're doing.